Yay, it's another note card reaction day. As you've probably learned to expect from these types of days, it's me just throwing a bunch of what seems like random reactions at you with no mechanisms that you can throw in a note card and hopefully memorize, I guess. And kind of the whole idea of most of these days is to give us some tools for really interesting synthetic strategies that'll actually be the next video lecture. So today's just random assortment of reactions will hopefully not be incredibly random because they're all going to have to do with these aromatic moieties. I should mention that kind of the first half of this video is going to be what I consider kind of benzylic reactions. And so let's talk about those. The important thing to recognize about the benzylic position, even though it sounds like benzene, it is actually benzene with an additional carbon. So anytime I talk about any sort of benzylic reaction, I am talking about a reaction that happens exactly one carbon out. This is a benzylic carbon, and it may have two L's, I can't honestly remember. So it turns out there's a whole host of really interesting reactivity having to do with this position that is right next to all these conjugated double bonds here, or I should say conjugated aromatic system here. And then the second part of what we're going to talk about today are known as coupling reactions. And I'll be totally honest, there are zillions of coupling reactions. I'm just going to highlight the ones that your text highlights just to kind of keep the madness at bay a little bit. I'll talk about each one, but what you're not going to notice in me talking about these different reactions are mechanisms. Not to say that they're never important, but they just don't have that same kind of generality that I really like to spend time in mechanisms with. So instead, we're just going to kind of end up with a nice pile of note cards at the end of this. Starting with these benzylic reactions, I'll try to group them by kind of what I think of as the most important and kind of work my way to the less important ones. I would say probably the most important benzylic reaction to know, and let's just start off with any benzene ring with anything else imagine on this ring. And what we're going to learn is a really effective way to put a halogen on here. And of course, the reason we put a halogen on there is that halogens tend to kind of present a sticky end in all kinds of different reactions, including SN2 reactions, and certainly in some of the organometallic reactions we'll talk about as coupling reactions. It's just a really useful thing, as we've seen before, to be able to introduce some sort of halogen in there. So there are actually two different ways that we can get to the product. And it turns out that both of these methods are initiated by radicals, right? Which means, if you remember way back to the first term, we talked about kind of a radical chain reaction with all of those weird little fishhook arrows and such. In other words, movements of one electron as opposed to the heterolytic ones that we see generally. I'm going to not talk about the mechanism just because it's really just the same that we've seen before in terms of like the radical reaction that, say, like an alkene would undergo. But the reagents that we're going to need here, either if we did it kind of the more old-fashioned way, they'd be represented like this, and this is read as Br2 in the presence of light, right? H nu is the way that organic chemists tend to represent light. And so oftentimes, anytime you have some sort of light present, as we mentioned back in the radical chemistry days, that's going to cause certain bonds to break homolytically. And so that's actually what's going to happen right there. Turns out that this particular reaction ends up putting a bromine on. I should mention that this benzylic position has a pretty similar reactivity to what's known as an allylic position, right? And so that's an allylic position. It turns out we could also put a bromine on an allylic position using the exact same reagents. So in terms of my learning, anytime that I saw some sort of benzylic radical process, I knew that just about every process that happens to a benzylic position in a radical mechanism also has this allylic analog. So that may be something that helps you out of a bind someday. And so there's a little bit of a fancier way of doing this reaction. And that is with something that is abbreviated as NBS, right? And NBS I think of as a source of Br dot. And its real job in the presence of light is kind of a more easily used source of Br than having, let's say, liquid bromine floating around that you have to add to your reaction, which is kind of a nasty thing. So these two things, right, that in terms of like memorizing, I just kind of had a red flag that went up and said, that's a source of bromine somewhere. I'm not going to worry too much about showing you the structure of this thing, other than to say that it is a source of that Br dot. Okay, so let's take a look at another important benzylic reaction. One thing that we haven't seen yet is a way that we can actually introduce some sort of carboxylic acid, right, to make some sort of benzoic acid. So it turns out that anytime you have any kind of aromatic ring that has a benzylic position, and by the way, I could actually put more carbons bonded out here, it turns out that I can very quickly convert any kind of benzylic position to the benzoic acid derivative, which hopefully you can see, right? So it's a way to take any kind of methyl or ethyl or any other kind of alkyl group out here through the addition of some sort of really strong oxidizing reagent. It turns out that you end up with carboxylic acids. There is kind of a related cleavage reaction, as I mentioned, where if you imagine, let's just say that we've got some sort of big long chain out here. Turns out that KMNO4 will cleave always at that exact position and leave behind carboxylic acids. And usually these cleavage reactions are not super helpful because you're kind of throwing away a bunch of molecular weight of your compound. But certainly something like this will be synthetically useful to us, because keep in mind that this is an orthopara activator in EAS, and we now have a way of pretty easily turning that into a meta director, and that is also deactivated. So hopefully these reactions will help you through a couple of difficulties. One issue we should definitely just be sure to just briefly talk about is that this benzylic halide, even though we would look at that and say, oh, it's a primary, it turns out that that primary position right there is not really a primary position, right? So in other words, so back when we were talking about like SN1E1 type reactions, we talked about the fact that primary carbocations are kind of avoided. Well, it turns out that once this bromine leaves and leaves behind a positive charge, the fact that I can then end up with a bunch of resonance hybrids actually makes this thing very likely to undergo certain SN1 mechanisms. And of course, if I put some more carbons out here, that would give rise to a whole bunch of E1 type mechanisms. It's also a really great SN2 substrate, it turns out. Very easy to attack. And so that's just something you'll definitely want to keep in mind. And of course, the first reaction we saw was how to actually put a bromine in there effectively. So coupling reactions, if I really did do a deep dive on this, would feel way too overwhelming. There's just so many different coupling reactions that are named out there that all have like very tiny differences between them and in terms of like when you'd use them. So I'm just going to stick to the ones that your text message mentions. And I should also mention that you could also call these coupling reactions, as your book I believe did, organometallic type reactions. We are actually going to study a whole host of organometallic type reactions kind of closer to the end of this term. This is really the first example of us talking about these things. And so I'm going to introduce, to start off with, kind of like 2A here, is we're going to talk about something called a Gilman reagent. And as you might expect, The reason we call these things organometallic is that they have an organic part and a metallic part, right? And those metallic parts are almost always, at least the more interesting reactions, are almost always made up of metals from the transition metal region of the periodic table. You might remember way back in Gen Chem, one of the big pains in the butt about transition metals is this idea that they don't really follow the same kind of, almost octet rules that we kind of that we typically talk about. They have all kinds of different oxidation states, and it turns out that's exactly what you want if you want some sort of catalytic organometallic process to happen. Not to say that they're all catalytic either, but you get the idea that multiple oxidation states are pretty helpful in terms of reactivity. So Gilman reagent, what are we looking for in a Gilman reagent? Well, it's any kind of organic part that I'm going to represent as an R. There's generally two of them, and this thing is actually itself, oops, I shouldn't do that. That's actually a minus charge. A Gilman reagent is actually a salt that has lithium as a counter ion, and it turns out that anytime you see this Gilman reagent, what it's trying to get you to recognize is whatever that R is, it's really kind of a functional equivalent of that organic piece with a minus charge, right? And a lot of times, students get really confused by the kind of the complexity of something like this. And I find it really helpful in terms of my, memorizing or thinking about these different processes to kind of remember what's its functional piece, right? What am I really trying to do? And honestly, the rest of it is just kind of around because it has to be there in order to ensure the same reactivity that we've come to expect from Gilman reagents. So what kind of, what's an example of maybe a reaction that involves something like this that'll allow us to do some aromatic chemistry? Here's a great example of the synthetic utility of a Gilman reagent. First of all, notice that my reactant here is actually itself some sort of halogenated compound, right? And so that halogenated compound with the use of a Gilman reagent that I just kind of picked out of nowhere, right? And so in this case, it's some sort of vinylic species. It turns out what can happen is whatever is in these parentheses is essentially going to displace that bromine, and we're going to end up with our product. And so what I mean by this coupling reaction, it's almost like you kind of took a piece of this and blocked it on to this, this aromatic ring. And the reason we're not talking about it is, let's say, an SN2 reaction is that we know SN2 reactions can't happen on aromatic rings. But what's actually happening, which by the way is not always terribly well understood, is like some very complex organometallic chemistry about the d orbitals of that copper compound. So one of the things that's true of coupling reactions is each one has like a different number of kind of limitations. Turns out Gilman reagents are really helpful and can react with a whole bunch of different things. Of course, for us, we're going to kind of concentrate on its ability to attack aromatic rings, but it turns out that as we go through the term, we'll learn that it's kind of a, I think of it as kind of like a softer way of using a carbanion to get some kind of more gentle reactions to occur, right? Eventually we'll start talking about Grignard reagents, and Grignard reagents are organometallic reagents that kind of do like anything that's just really hard and tough and just, absolutely kills starting materials. Whereas Gilman reagents, at least somewhere on your note card, put like, the more gentle choice. This is just one example. Let's go on to two different coupling reactions. And of course, we'll see Gilman reagents again and again and again in other contexts throughout the term. One thing I should mention is how you prep these Gilman reagents is really specific, and you can take a glance at your book. It usually involves starting off with itself, some sort of halogen that you treat with a couple of equivalents of lithium, and then you hit it with some sort of copper 1 salt, right? We remember back from the Sandmeyer reaction video that copper 1 salts are pretty helpful in terms of doing some really interesting things. And so take a glance at that if you're interested. The Heck coupling or the Heck reaction is a pretty iconic type of organometallic reaction. So each one of these named reactions, of course, use some different combination of reagents, right? So what we're going to be looking at for the Heck reaction is it almost always involves some sort of palladium-2 salt, right? In this case, just because it was, I think the most primary one in your book, I'm going to use a palladium acetate salt. The Heck reaction almost always has some sort of triphenylphosphine that's present as a ligand that contributes to that kind of the d orbital reactivity of that palladium, and then usually some sort of organic base like triethylamine or something like that. So that is the way that we kind of produce the reactive species, right? We're going to have that palladium insert itself into this, once again, halogen aromatic compound here. And then what we're going to do in typically a second step, or sometimes you can just include it right in the reaction mix, is usually to introduce some sort of vinylic system, right? Some sort of double bond. And it turns out what the Heck reaction is really, really good at is almost always in a trans fashion is kind of figuring out a way to have this carbon, right, that H, be replaced by this entire group right here. As I said, the mechanism is, I don't say, like, it's involved, right? But there's not much explanatory power there, so I'm not going to talk about it. Has a lot of organometallic chemistry, which has very different looking mechanisms. But the advantage of this thing is it's kind of a way of you just starting off with a boring old looking either vinylic or even like an alkynyl type H, right? This could also be a reagent in a Heck reaction. And what we can do is we can have this entire aromatic ring pop on where one of those H's was. And again, I'm running out of space like a silly person here. But it's a very easy way of getting like a pretty complex looking product to occur. And it also seems to be pretty insensitive to what kind of craziness is happening out here, right? So there are examples of using esters and carboxylic acids, a lot of structures, by the way, that have a lot of problems with different reagents. The Heck reaction is just like a really good reaction to choose to introduce new aromatic pieces into a ring. And again, right, this is why we talk about halogenation as like such an important thing, because it opens the door for all of these things. Obviously, if this was our reagent, we would have, instead of activating that H, we would have activated this H, and that's a way to get that triple bond right onto that, that ring. So take a look at a couple of the examples in your book, and it'll really start to expand your mind in terms of different ways that we can do some really cool synthetic reactions. Last reaction we'll talk about today is what's called the Suzuki coupling, or the Suzuki reaction. And one of the things that one of the things you'll start to notice is the reason that I don't go into all of the crazy names, because you'll notice that I even started with the exact same starting material, and I'm even going to put a palladium in here, right? And so you're going to say, oh, that looks a lot like a Heck reaction, right? Well, it turns out, no, it's not a Heck reaction, because instead of just using some sort of plain vinylic type species, what I'll do is I'm going to use boron. And I'm going to create what's called a borate ester, right? And so you can identify a Suzuki pretty quickly, because you'll now have a palladium with a little bit of boron, and attached to this boron is some sort of interesting vinylic or aromatic species, right? Let's just, write it like that, right? Back when we were talking about, let's say, anti-Markovnikov addition of OHs to alkenes, right? You remember boron is really good at kind of adding to different moieties, right? In that case, it was actually that double bond. And it turns out that the ester here kind of just moderates the reactivity of the boron. And coupled with this, the presence of palladium, and by the way, that's palladium on carbon, right? Which is common in order to like lower the price of your catalyst, because you can then reclaim it, right? And you can just kind of like filter out the little carbon nanoparticles that have the palladium on it. And what we're going to do is we're going to take whatever is bonded to this boron and once again, just like in the Heck reaction, kind of plop it on to that entire moiety right there. And one of the things that you'll notice is that we're able to fairly tightly control the stereochemistry of what of the orientation of these different groups. In other words, however it's attached to the boron will be exactly how we attach it to the aromatic species here. And again, there's a pretty good section of your book that talks about the ways that you can actually produce these borate esters. And not surprisingly, many of them involve you doing some sort of modified boron type addition to like a double bond or a triple bond, right? So we're all kind of coming full circle here. And so you can kind of see the madness, right? The second that somebody comes up with some other way of using palladium or some other catalyst, and gets to name it, right? And so that's why, like in grad school, my mind was always swimming. I could never remember these people's names. I could remember how to do things, but I could never remember the names of all these things. And of course, each one of them, like I said, has kind of ins and outs that you kind of have to know about. So I don't want to bore you with that. I just kind of wanted to show you the kind of pretty interesting set of reactions that are known as organometallic reactions. So the next time I talk to you, we're going to be hopefully using a bunch of these in some really cool synthetic problems.